this quickly. Good morning, everyone. Welcome back to another lecture of AI-based decision support 1, the basics. So as always, let me quickly summarize what we did so far. Or basically the last lecture. So summarizing everything would be quite a task. But putting it into perspective, what we did was we uh, we basically worked through the parts of the crisp DM process. So at the beginning, I gave you a short introduction. Why do we do this? How can we support decisions with predictive modeling, which is our focus, more specifically supervised learning, which is the focus of this course. And within the modeling later, you will see we also again narrow it down to shallow machine learning to get the concept. And in AI BDS2, we will talk about deep learning. So, but for now, we didn't start at the modeling stage, right? We did start at the business understanding stage, and from a business understanding perspective, we formulated a goal and some precursors, some ideas on how we want the solution to look like. So basically, business understanding tells us how does the solution look like, right? So how does it need to look like, better to say. So then it's our job to work towards that. So and we said, okay, it's a data analytical problem. We transform the business problem and we call it data mining, or the crisp DM process called it data mining problem. You can call it data analytic problem, data science problem, whatever you like. It's up to you. The main thing is that we have to translate from the domain language of the people that we are working for, the people we build the model for, that have the domain knowledge, into our language, which is the language of data science or AI-based decision support, or whatever you want to call it. So the data analytics language, business analytics. So, and then we went on to data understanding, said, okay, what kind of data do we have? What is data actually? How do we need to look at data? Specifically, how do we need to diagnose the whole thing? If sometimes we have scenarios in the data that are not going well. And this will be very handy for us, especially specifically today when we talk about data preparation. So how can we actually fix some of the problems that we have? So we will combine data understanding with data preparation. As I said, it's a loop, because what happens if we do not go into these steps? Like what happens if we go directly through every data in and go directly into modeling? Well, we discussed this with the Anscombe data set last time. This is why I put the slide on at the beginning today. And we said that some problems like outliers here in case 3 and 4, or model specific or model misspecification. So this here, case 2, is a model problem. So this is a problem in the modeling step where we actually did not fit the data well. So this has nothing to do with data preprocessing. However, data understanding will give us maybe an idea on how the data looks like or how the data behaves. However, this is actually kind of hard to detect, and this is why I wanted to show you this. So if you may allow me one remark specifically with this case. So since these cases, okay, this is all right. This is a data preparation problem, but this is a modeling problem. And I told you at the beginning when we were discussing data understanding and we were discussing bivariate analysis, I said, okay, we might not want to focus too deeply on the bivariate analysis as you do in statistics. Because in statistics, we heavily use correlation, significance tests, and so on. Specifically, correlation would be a problem here, because the correlation coefficients that we know, they are looking at linear correlation, right? You have to know from the formulas linear correlation. Now, of course, we can propose any other form. So we can propose any other model and see if it fits, but this would be guessing in the dark, right? So this is like a problem. And this is ultimately basically one of the problems that will lead us into deep learning. Because what we could do, like if we formulate a model, we could get x2 squared in here, which would fit. Like I think or minus x2 squared in this case, so minus beta, and we have x2 squared here, right? Because as you can see, this is clearly a quadratic, and most of you mentioned this last time, that this is not befitting, the blue line is not befitting the data. And so, but now you would ask, as a clever student, and think all of you have this question in mind, but how can we see it? I mean, come on, Kai, this is two-dimensional data. We don't have this. You told us about sensor data, about large data tables. You even uploaded an example with a lot of columns. So how is this possible? The answer is it is, right? So we won't get these things from data understanding. I've got to be honest with you. You're never going to see this unless you have like a two-dimensional data or you look at a lot of correlations, a lot of scatter plots. So sometimes we can do this if we look at all the scatter plots and we see this kind of relationship. We can basically look at this because the only thing we're interested is the target variable, which is always here, and then we have to plot this thing for all the other variables that we have. Right, so either I get a clever way of summarizing the variables, or I will have a lot of these plots to examine. Now, if I have cases where I have limited number of columns, then I might be able to do this. So sometimes I have standard problems where I can say, oh, this is pretty okay. Like 100 variables, it's still okay to look at 100 images and you see it okay. Or split it up in a group. So this is still okay. So you can do the data understanding, but for the most of the heavy cases later on, the data heavy cases with a lot of columns, this becomes unfeasible, right? Because we usually don't have only one variable. And in addition to that, what you have to know is that just because one variable has a quadratic thing, we don't know about the interaction with other variables, right? So this is our target variable and it gets influenced by, let's say, 10 variables. There's an interplay between these 10 variables. So for example, variable x1 and x2, they might not do anything alone, but if x1 has a certain value and if x2 has a certain value, this is maybe the combination where y gets heavily influenced. Like for example, when the temperature and the vibration are both at a high level, only then there will be an error, for example. But if the temperature is high, no one cares. If the vibration is high, no one cares. But the interaction is the thing causing maybe an error. So we don't only have to care about this, but also the interactions, and it could be quadratic, and it could be crazy interactions, right? So it could be x squared times whatever, right? x1 squared, x1 to the power of 3, whatever. It could be triple interactions even, like x1 squared times x2 to the power of 3 times x3. So just to make sure that we will revisit this in the modeling where it belongs. And I will show you ways how to deal with that if we have like tabular data where this is manageable. And ultimately, I can spoiler is if this is not manageable anymore, for example, in image data. Like in image data, we have every pixel is like a column and a row. So we have pixels in columns and rows. And this is just one image out of our whole training set. So one image in our training set, I have for each pixel, I have a variable. If I have 100 times 100, I have that many variables. Usually I have thousands. You know the resolution of nowadays images, they are not 100 times 100, but they are more pixels than that. And I have that many amount of, would have that many amount of columns, but we will find other ways to circumvent the whole thing. To circumvent these problems. But I can tell you the spoiler is for unstructured data, for a lot of data. For example, time series data comes in really fast. We have a lot of rows, and especially when I have a lot of variables, deep learning will be the way to go. We will sacrifice some of the automated work we have for shallow machine learning for manual work preparing this. However, we will have less to prepare and more model configuration to do. So the work that gets more infeasible will be basically put into the hands of the algorithm, but we have to care more about how to I'm not using the word fine tune, but how to configure the algorithm. Let's say it that way, because fine tuning is a reserved term. You might know this from GPT models, so I won't use it. In the past, we could use it, right? But it's not the right word because fine tuning is a whole nother thing. Okay, so long talk, but the actual thing is, so we do care about these things, right? This is a modeling thing. This is okay-ish. And today we're going to discuss what's all about data preparation. So first of all, I split this up kind of, and I want the focus like, we cannot do everything. So I'm just gonna dip into it a little bit because this is like you have to imagine data preparation. So the things you can do in data preparation it's immense, right? You can do basically everything you want. And this is a hands-on thing. And more specifically, this is like tools that you learn and also through experience. So remember when I told you to use that RapidMiner software to play around with the processes and specifically have like these pre-processing things, or play around with Python also. We offer some we had some assignments regarding data preparation in Python, and you can extend this as you like, or you can go through the HR example and have data understanding, and then start preparing the data if you like, and see what you can improve actually. So we will focus on these three categories, and we will have some of the tools or of the tool categories what you can do. So I will introduce the general categories. However, I'm not able to introduce every single tool that there is. So just know that this is experience you gain and say, oh, I could do this. Maybe I could do this. Maybe I could do this. And then you see how it plays out, right? You see how the model improves or not. And then you see if your step was right or wrong. So as I said, there's a lot of trial and error. I know students don't like to hear this. They want to hear, if you do this, then this will be cool, right? But it's not. It's just not. And it probably never will be. Like there are some things where you can say this could potentially be a better thing to do. Like we will talk about this in discretization, normalization, but usually it always also has a downside. Like for example, loss of information or something. Or also missing values has a downside if we just like do different things. But it also has upsides. So usually, and this is the hard part for you, you can basically discuss these things, right? So one of you could tell me, I don't want to get rid of the missing values, or I want to just impute them. And I said, no, we need to get rid of them. And both of us will have a point, basically, right? Sometimes it will be in favor. The data situation will be so extreme that it will be in favor of either one. But usually it's like mixed, okay? And we have to make a decision that again comes from the business goal. So we have to see what's best for the business goal, what's best, what do we need, what do we want, how does the situation look like? And this is where data understanding comes in. This is why I said this is a closed loop. So again, we have data transformation. So data transformation means we actually change some variables in their nature. So this means data transformation is usually about the column. So we usually change a column, and we usually squish it, we normalize it, we can even multiply it, so we can generate a new variable. For example, here I could simply build a new column that is called x2 squared, which is just calculated as x2 squared, right? So I can add a new column, and this would also be like data. Yeah, this would also, sometimes this is called feature generation. So when I add a new feature, this is sometimes called feature generation, or the whole process of making available new features, new variable that can improve my model is called feature engineering. I think this is like a pretty cool thing to do. Let me just quickly. This is feature engineering, and I think this is probably one of the words that you will hear most often. So this is you might not remember it at the beginning. There was this in the introduction slides. There was this video about data-centric AI, and this is all about feature engineering. So instead of like configuring a lot in the models and using different models, we ought to take also care of the data. This is why these steps are so important. And feature engineering, like getting external data or transforming data that we have, like a simple example would be x squared. Another example would just be, let me give you another example of creating a variable. So let's say you have this date variable. So for example, you have a date of purchase. So let's call it date P. This is the date of purchase. So you have customer ID, and this is the date of the last purchase, right? So this is a cool thing. So this is like 23 of March, right? This year, maybe 24. And so this is customer ID 1. And this is customer ID 2. And the last purchase was the 11th of November this year, right? And so on, okay? So, and this is basically what we could think of. And third maybe was the 3rd January this year and so on. Now, the problem is these date variables, like you have to imagine what we want to do is we want to build a model based on the features. So this will be part of somehow this could be one of the features. Now in feature engineering, right? Feature engineering. In feature engineering, what could we do with this to make it a better variable? What would be a better idea? I want to give you first a general idea on what we could do in feature engineering, right? Feature engineering belongs to data transformation. So this is a subcategory, right? We could put it right here if you want, right? What would be a better way on putting this in here? Like what would be more interesting if we want to predict, for example, why, for example, could be is the next purchase like was there a purchase in the next like 1 week, like in like for example how much money did the person spend on like at the point time in t, right? So this is like at t or the last 2 weeks, last 2 weeks, money is spent, right? And this is what we want to predict. So we want to predict for the people, are they going to spend? Are they willing to spend any money? So we're going to send them some advertisement, right? So this is the idea, right? This could also be just, did they buy something? Yes, no. This could also be like, either this could be the money value, like $100, or this could be just like, yes, no. Like it depends on the business case. But either way, what would be a better way on putting the date in there? Because the problem is the date. What is the date? What data type? We're going to start analytically. Like we now have this analytical task as we always start our lectures. What kind of data type is date actually? So what kind, we only, the variable types, right? So nominal, ordinal, numerical, right? So numerical having ratio and interval scale. So what kind of scale is this from these three? Like there is no date scale, right? So what kind of date is this? What kind of scale is this? Like what can we do? Like what kind of scale is this? This is like a question you could ask yourself, right? Like what kind of scale is this? And then ask yourself, what could we do? Like what could we do to improve this? How could we also express that, right? So how could we also express that using other knowledge that we have, right? So let me give you another. So maybe today, what date is today? Let me see. Today is the 3rd of December. So knowing that today is the 3rd of December. All right. So how else could we express this? How could we get a new feature in here? What could this new feature be, right? You have to ask yourself right now. I'm going to give you some time and I want you to think about this in the context of this prediction task. Like the question is, will they spend money on our product? So these are customers that have spent money. For example, we have an online shop and let's say we sell coffee beans, because this is my prime example, because I buy coffee beans over the internet and they pretty much know exactly when I'm out of coffee beans. So this is pretty cool actually. So they like I have like some left and they just said, hey, you get a discount, order now. And I always use this, like, because why not, right? So this is the task. Okay, go. Can write in the chat. How can we transform this? Think about it. You can again think very easy. You probably all think too complex. But this is basically the only way I can teach you how to do this, like through experience, through examples, because it's a hands-on thing. And also there are some algorithms that we will talk about in a few seconds. So I'm talking about date. date of last purchase. What would be a new variable, like a new variable, the question mark variable here, that I can generate based on that? Come on. I'm gonna wait till someone says something because this is like more important than teaching you this. Days since last new days since last purchase. Perfect. Yes, exactly. Days since last purchase. Maybe the recency, which is the same. Yeah, exactly. Good job. Yeah, exactly. So instead of having the date, which is an ordinal variable, I mean, I can say, okay, I can order them, but this is really bad. I cannot put it as an X here. So what am I gonna do? I'm gonna do like, how does my model gonna look like? I mean, beta 0. Okay, this is a constant and my first variable is 22.3. Like, how do I, this is not possible. Like what I could do, basically, I could transform this like into a number, like the computer does. However, this might not be very good. So I have to transform this somehow. And a good way in transforming this is I'm not going to use this variable, but I'm going to transform this into a new variable that is called days since last purchase, right? So, and then I can like easily compare this and I can easily say, okay, this is like 90 plus 3. This is like, for example, 22 days, and the rest I will not calculate, or maybe it's 23 days. I'm not sure, but it should be 22 days. So, and then I can build upon that, right? So, what could also be important? Like, what's another variable I could build in here? Like not based on that, but just another variable that would be cool to have. Let's say I don't have it, but what would be a good variable to have here? Like, think about it. We want to, at the end, what kind of decision do we want to make? We want to decide if we send someone a discount or something that they can use, or maybe a catalog or whatever. So we will have some effort behind it. So what would be another thing that would interest us here? Like we have the date of the last purchase. What else would be interesting? Like just out of your head, if you have to search the database, what else would be good variables? So this is actually feature engineering through looking in the database if we have the data. So we don't need to engineer the data now. Just out of your head. You can be very creative here. Let's look. There are a lot of answers. Okay, amount of last purchase. Yes, exactly. Amount. That is right. So other variables, I'm gonna make it here. Amount of last purchase. Amount LP. Perfect. Yes. How many products they buy? Yes, exactly. Number of products. So this is important. You might not say, okay, yeah, but I care if they buy large or small products. No, it's very important. Like, do they buy everything at your site, or do they just buy particular products, no matter what is? So, and this brings you also how many products ordered last, amounts of last transaction. Yeah, perfect. So, but this goes on and on. You can also see like type of, like you can extract maybe some type of products or the dominant category of products. Jesus. Dominant category of products in last purchase, right? Or and then also what you can have, so these are all last purchase related, but you can then also have like general things. Like you can what are general things that are not related to the last purchase that adhere to the customer? And they could also be similar, like lifetime amount spent. Like you have this concept, customer lifetime value. You heard it maybe in marketing. Like what's the total amount spent of this customer? And then what kind of products does he or she do they usually buy, right? And then specifically the last purchase, because things could change, right? So, for example, when I order at the coffee place, right, where I order my beans, I also order like cleaning products for my coffee machine because this is like a convenient thing for me. It's just a convenient thing for me to order them together. And because otherwise I would have to go to another platform and there I have to search it and I need a couple of cleaning products. It's very complicated and I hate it actually. But there I can just say, okay, last purchase, and I can just click it and it's convenient for me. I save time and it's not, and with a discount, it's even less expensive, to be honest, than when I order it, for example, from Amazon or something. And what happened last time is, so they made the decision to take the cleaning products out of their inventory, right? So last time I wanted to purchase, as always, I want to purchase the beans and the cleaning products because I usually have them so that I need them like every half a year or quarter of a year. I need it all together, and they removed it, right? They removed the cleaning product. So what did I have to do? I had to go to Amazon or some other place, and I had to order them there, which was kind of a hassle for me. It's not a big deal. I'm just saying, right? It's not as good as it was. So somehow they made the strategic decision to throw these products out, right? For whatever was the reason. And this is like a business understanding thing. Like business understanding is first and almost a decision. So this is like a little business discussion, but I want to discuss with you in the next maybe 2 minutes, and then we're gonna move on to the technical part. Why did they make the decision, or what could have data driven? This is called, like you see, this is called data driven decision support. So what kind of data could have driven them to take these out? So it could be, first, let's start with data driven reasons. They don't have to be data driven, and we will discuss non-data driven reasons later. So taking my small example from my own experience, and you can do the same. After the lecture, think about things where I said, oh, this could have been a data-driven decision. And even if, like, for example, if you discover bad decisions, like think about how would data lead to that, and maybe then you discover that data did not lead, they did not look at the data, maybe they just decided it, or maybe an external force forced them to. So maybe the supplier of the cleaning products wasn't like giving them any more discounts. Like they said, oh, no, we want to sell it more on Amazon because they are larger. We don't want you to sell these products, and we don't give you discount. Then for them, it's not profitable anymore. However, what could be data driven? What could be a data driven reason for them to have taken out the coffee machine cleaning products? Like what could be a data driven reason? Like we have some variables here, right? So then we can aggregate these variables also over all the customers. Think about it. This is data understanding while we're doing what we're doing now. This is also a little bit of BI, right? That we do now. Remember, this is now explorative analytics. But I just want you to show that this is important. Like data understanding or explorative analytics is important. So we're focusing here on predictive analytics. However, from time to time, I want you to think, I want you to just leave where we are and go into the decision, because the decisions are the most important things in business, or probably in life, right? So knowing the process, knowing the decision, making the decision based on data. So just quickly give me 1 or 2 reasons why would they throw out the cleaning products from their inventory. I mean, you're all business students. You should actually also know from other classes. So if we have an exam right now, a business exam, and you're all like master level, maybe you're not. Okay, if you're from other faculties, sorry, but I feel like you can also think this one up. So it's not that difficult. But yeah, okay, they sold only few products of this category recently. Yeah. Is it how we understand data based on business purpose, like what we want for business decisions? Yeah. So my question was like, I presented to you a case, like a business case, and I wanted to know, I don't know the truth. This is very important. I don't know the truth. So I want you just so I cannot tell you if it's right or wrong, but I want you to speculate a little bit, since this is the way. Like if you do all this we do now, this is like business understanding. Like this is hardcore business understanding right now. You have to know, why do people make decisions and how can I support them with data? Usually you come into a company and you are the one implementing the data-driven decision support. This is why we teach you this. And if you cannot connect the things they want with the things we teach, then you have a problem in practice. So yeah, exactly. So this is how we understand. Database means they get the information from the database and then they make their decision. So database means they could also have a prediction model. Like they could have a prediction model and say, okay, a prediction model that says this is the sales. sales for the next year. So this is the sales for T+1, given that the product is cleaner, that the product is a cleaner product. Okay, I make it really easy. And so, yeah, or just make a comma here. Don't want to let this look like a probability, which is it's not. So just okay. Sales in next year, and then they have a prediction model for that, and they predict the sales will be like they will only sell 20, which is ridiculous, but I'm just saying 20, okay? And then they say, oh, the predictions vary. So, and then they can calculate the costs, blah, blah, blah. And they say, okay, actually the costs we need to sell them and we need to purchase them in bulk. Otherwise, we don't get a discount. And if we don't have them, then we don't really earn the amount of money that we want. So we concentrate more on the coffee bean business and making relations with these kind of suppliers rather than the cleaning things, right? So, which is weird because they also sell the coffee machines. So this is what I don't understand. But however, okay, maybe they want to direct the customers to buy their core products if they are more profitable. Yes, this could be. So they basically so it could be that I don't know if there is an effect. So I'm not a marketing expert. So if you are a marketing expert, please speak out or Google it. Is there an effect that says if someone has like this whole inventory, a large inventory, like you notice when you go to a restaurant and they have like this menu with they have schnitzel, they have döner, they have pizza, and you think this cannot be good, right? Nobody can make everything. So you want rather go to like a schnitzel place that only has schnitzel or that only has döner or burger or vegan salads, or yeah, salads are usually vegan, but yeah. Okay, so you know what I mean, right? So if there is such an effect, then this could go into this direction, like but yeah, it will probably be a mixture of it. Okay, so just so this was like an introduction on why you need some gut feeling and some creativity to come up with this. So it makes more sense, but I see you have it under control. And then there are some other things you can and you need to do. So let's start with data transformation. So this is the first we will discuss, data transformation. And the first thing is something where you would initially say, why do we actually do this? It's pretty counterproductive in the first, because a discretization, what it does is it transforms a variable, a numerical variable, so to say, so it's either interval scale or ratio scaled, into a discrete variable. So it basically changes the domain of the variable from like infinite, minus infinite to plus infinite, or maybe just doesn't have to be that, but usually is, to basically have only a few values to some categories, right? And the idea behind this, how to do this, is basically to build a histogram. When you remember how to build a histogram, so basically what you do is if you have like a continuous value, so this is like your data that you have, and your data points can lie on wherever, right? So some of them are here, concentrated here, then there's maybe some points here and there. So this is like and they can lie on this wherever they want, right? And now what you do is, and this variable, this is the variable that it looks like. This is the original variable. Let's call it x1, right? And like we have x1 transformed. I'm going to call it x1 underscore transformed, tr. And x1 is some value, right? So these are examples from values. So these are values from x1. So don't get confused by this underscore. So we changed it. This is just this is the row now. This is actually the row number, not the variable number. So we just transposed it. So don't get like nervous. These are not single variables. So these are like values in here. So if I transform this would be 64, 65, 68. So of course they are not ordered, right? So it could be like that the 80 is here and so on. So I just ordered them because this is what you usually do before you transformed. But this is the original variable. And then what we would just have some class, right? We would just have some classes. So, and we could name them. Like, obviously here we have intervals, but we could name them. So we could either number them, right, which is kind of dangerous, but yeah, we could do this. So we could just name them 1, 2, 3, 4, 5, 6, 7, right? So we can, and this variable right here now has a group. So we know we have 64, 65, we have 68. So we know that this is in group 1. This is also in group 1. This is 68 is in group 2, right? You can see this here is in group 2. And 80, let me see, is in group 6. So, and this would be the transformation, right? I just want to show you how in practice it would look like if we transform x1 into x1 transform, like if we do a discretization. So this is a discrete variation using what we call equal width binning, which I will explain in a second. So how do we get from here? I'll explain in a second. But first, I want to discuss the why, because this is the pressing question you have. Like, why would we actually do this, right? Like, why would we do this? Do you have answers to that? Why would we do this? Because it is obvious, and I don't have to tell you. We lose some information here. Like, for example, we lose the difference between these two. We lose the difference information. Like, this is variation. We talked about variation, how it can contribute, how different values and different combination. I just talked like for 5 minutes non-stop at the beginning of this lecture, how combination of variables, blah, blah, blah. So I gave you a very lame talk about how everything influences everything and the combination of variables. And now I'm saying, but we can like reduce this a little bit. Like we could reduce this information by building groups. So for example, we would lose this difference. We would actually also lose this difference. We would also lose this difference, because why would we lose this? And for this, you have to ask yourself, what kind of scale, like we learned the scales in data understanding, like what is data, what are the scales, what kind of scale is x1 here? So it's temperature, right? So it's temperature. So it's a numerical scale, right? Let's call it numerical. Let's not get into details of ratio and Fahrenheit and Kelvin. So sometimes they have a zero, sometimes not. Let's just say this is numerical. What kind of scale is this? What kind of scale is x1 transformed? This is, by the way, a prime exam question. Like I give you exactly this, and I say, okay, hello guys, I did a data transformation. I used equal width binning. Or actually, you have to use equal width binning. That would be even sweeter, so I don't have to do this. So I can get you more points even. So I give you this variable, and I tell you to do equal width binning. And then you're going to write me these 4 values, and I'm going to ask you, what kind of scale is this? And you need to answer that. So this is a prime exam question. And what kind of scale is it? You have 3 to choose from. This is numerical. We know this, right? So actually it's interval, but yeah, we call it numerical. It will be fine. What kind of scale is this? This has to be faster, guys and girls. You need to know this. What kind of scale is it? Think about what can we do with it? What can we do with it? Yes, it's ordinal scale. It's ordinal scale, yeah. So it's ordinal scale. So first of all, it's ordinal because we lose the ability to interpret intervals. So we don't know the difference between 1 and 2. We don't know the exact numerical difference. But what do we know is that 1 is smaller than 2 in terms of temperature, right? So this temperature is lower. This temperature is lower than that. This we know. So we have some kind of order. We can order them. But we lost the scale level. So we cannot, for example, now we cannot calculate averages. We will get a lot of problems if we put this into a model now, right? Because this is actually an ordinal variable, right? And as a data type, this will be considered as an ordinal input variable. And basically, usually the data mining tools, they don't care for ordinal. Like in statistics, there are some cool ways on dealing with this. But to be honest, in Python, this will just be polynomial. They will just say, okay, this is like this is a group variable. This is a grouping variable. Like they just go, okay, is it like an integer, or they just go with data types, and usually you have something like groups. But yeah, there are some tools, obviously, also in Python to say this is a nominal variable, but the algorithms, the deep learning and the shallow learning, they don't really care. They just look at this and say, okay, right? So you either have to decide if this then gets numerical, or so because you are more interested in the ordering, or you're more interested in the grouping. However, one important thing is that why do we do this? So some methods require discrete values. So like if we have like naive Bayes, or we have some trees, and sometimes they are nicer to look at, to be honest. So sometimes it's just a feeling that you have, where you say, okay, where the numerical values really don't do anything for you, because it's like just a slight change. But if you have like groups, you can like interpret the models better. Because if you have like here, let's say we have 3 groups, like this is group 1, 2, and 3. We could say that, for example, and then we have a prediction, some prediction variable y, some prediction of y, and then we can say, okay, the prediction of y goes up when it's group 1, and goes up when it's group 1, and it goes usually down when it's group 2, and in group 3, and in group 2 it's a little bit mixed, right? So for example, so we cannot really tell. But so having not done that, this would be harder to do, because we cannot really say, okay, what we want to do is when the value goes up, it goes down usually. This would be our idea, right? But in the group, we can have a better interpretation. And like if we have naive Bayes, or we have some kind of decision tree, like it's cooler to say, hey, this is like we only have like 3 groups. So 1, 2, 3. So this is the variable here. So we start with this variable here, v. So if this is 1, then we take another variable like x. And then we have, this is also like, it's better readable. Otherwise, I have to do, in decision trees, I would have to do the split anyway. So the decision tree would usually also say, like, this is smaller than 10, this is larger, equal to 10, and smaller than 12, for example, and this is like larger than 12. So we would have to do this anyway. So sometimes this is cooler if we do it ourselves. Also, we can reduce data size. This is some kind of thing. So this is like, we don't have, we lose variability, but it's more enjoyable to look at, right? So for the interpretation, we can prepare for further analysis. Like we could also use this in data understanding better. So if we have like an easier way to look at, and yeah, for summary of data, as I said, we can just have these groups and we will have the summary, right? So this is also called binning. This is the same what we do in histogram. And basically there are 2 methods that we can do. So we have equal width binning. So as you can see, these bins here, every bin has a height, right? This is the height. This is the height. And this is the width of the bin. And equal width binning says everything. That means that the width, so how wide they are, is always the same. So here it's always 3, right? 64 to 67 is 3, right? They always have like 3, they always have a temperature of 3 degrees. So, and then we put in there however many values we have. So if we have here, for example, we have 2 values that fall within this bin, then we have 2 that fall within this bin. And by bin, I really want you to imagine a bin having bins in front of you. And the bin has like a label on it, and it says, here you put in all the data where the temperature variable is between 64 and 67, right? And then you have the other thing where you say, okay, or let's say 66, like, because it depends because of this, right? So, and then you change it, and then you have the next bin and says, okay, here you have 67 till, for example, 69.99. So as long as it's not 70. And beginning at 70, you will start this, and so on. And then you look at the label, and then you sort it. This is the job. This is basically what you do. Like this is the job of this is how it would look like if a human does equal width binning. Like first of all, the first step is you create the bins, right? Bins of equal width, and then you sort the data into it. Sort into bins. And the only thing you need to know, you need to fix here is the width. Like this is something you decide, right? So the width here is something you decide. And this concept of something you decide, I will use very often, right? So, and it's very important that you memorize what you need to do and what the computer does, right? So this means the width is something you need to do, and the process is something the computer does, right? For you. So it's a function in Python. But you need to give this as a functional value. You need to give this value. There might be a standard value, but this is still something you have to decide, right? In terms of machine learning, when we configure machine learning models, like this is called a hyperparameter. It's not basically called a hyperparameter in this case, or it's voluntarily hyperparameter. But I would suggest you, whenever there's something you need to do, to call it a hyperparameter, right? So a hyperparameter is something you need to do. It's like a setting. It's like a setting in a game, or it's like a setting when you whenever you want to prepare something, this is something you need to do, right? So in a recipe, when it says, okay, bake at 20 degrees, or let's say 200, nobody bakes at 20 degrees, stupid, 200 degrees, the oven will bake it for you. But what's the hyperparameter here? What's the thing you can do? Quickly put it in the chat. So when you bake something, what's the hyperparameter? This is the thing you need to do. The oven bakes, right? The oven does it for you. But what do you need to tell the oven? What are the hyperparameters in baking? The temperature, yeah. Yeah, temperature, right. Can also say the time, yeah. So if the oven says, okay, we can also have the time, like if the oven says, okay, I'll bake it for 20 minutes. But it could also be your manual labor to look frequently at the oven. So this depends, but yeah, time could also be reasonable, and also be the mode of operation. Like for example, is it I have no idea how it's called. Like, is it a grill function, or is it the other function like in the oven? Like these are hyperparameters. And I think with this analogy, we will always remember, like these are things that you have to set, right? And we will also see that in deep learning, we will have to do, like in the modeling step, some methods require a lot of them, and some methods do not require a lot of them. But other methods require a lot of manual work, like kneading the dough. Like this is manual work. Like this is a nice analogy. Like you need to prepare the dough, right? This is a lot of manual work. But you can also use the KitchenAid, throw everything in, and the KitchenAid will like put your dough. But then you have, again, what you have to do, you have to configure the KitchenAid. How long? Which intensity? Remember, this is the prime analogy. Like you save manual labor knitting the dough, but you have to configure more. Same thing with the time. Like, for example, when you say, okay, this needs to bake at 200 degrees for 25 minutes. Like you can set the timer, and maybe the oven says, okay, or you have like an intelligent thermostat that says, okay, after 20 minutes, you go down to 180, and then you're gonna turn off, right? So you don't have to care. You just have to take the cake out of the oven, right? However, you have to configure that, right? So instead of you going to the oven all the time, looking at it, what you do is you configure it, and it will be done. But as you can see, the labor that you have to do is shifted. And if your manual labor outweighs the value of the configuration, this is the difference between shallow and deep learning. But we will get to this later. But it was a nice way of telling you what a hyperparameter is, and that you have to set this with. And I guess you can see what equal height binning is. Yeah. So for equal width binning, if A and B are the lowest and highest value of the attribute, the width of the intervals will be. So of course you can like calculate the width of the intervals also, like if you like, but you can also, so if you want like an equal distribution, or sometimes you can also set this like in a histogram. You can calculate this, so you can let a formula calculate this. So you can also put this as into the hands of the machine. Like you can calculate this, and here you will get equal widths, right? But you can also say you can also like totally manually set this, right? So you can say, okay, yeah, I'm gonna set the intervals as I like, right? So or just say, okay, we want the first intervals to be equal, and then and equal height binning. So I will show you the idea of equal height binning. Wait, there's a question. How do we know when to use each method? Yeah, this is what this slide is about. So Lynn, I can calm you down. This is what exactly this slide is about. So I will explain equal height and equal width binning and the verses here, and then how you can choose. Okay. All right. So this is my example. Now we have an example for equal width binning, and now the variable here is some kind of income. You can see this the variable that we want to transform. So we're still in data transformation, and the variable we want to transform is income. Okay. And you can see here what we have here is we use equal width binning. Like we use equal width binning, and we use that formula here. We use that formula. So, and we look at the data, and what we have is we have like most of the people, they earn between 0 and 200,000. And then we have here between 200 and 400,000, 400 and 600,000, 600, 800,000, 1 million, and so on. And this is like between 1.8 million and 2 million. We have one person. So our width is 200,000. Our calculated width here is 200,000. And the problem here is, well, the problem is apparent, I think. So in equal width binning, what would happen using this kind of data? So I always like to draw it as a data table because this is what you get. This would result this is our transformed variable. So this is x transformed, like this is that. So let's call this 1 and let's call this 2. To make it easier, let's give these groups names so I don't have to write the intervals. This is group 1, this is group 2. So this thing, like let's say we have 500 people in here, or 1,000 people in here. So we have 999 times 1, and somewhere in between there is a 2, and the rest is 1. So here we lose a lot of information. So you have to like look at the distribution after the binning. Like you have to look at the distribution. You could look, for example, at the pie chart of the groups, right? So, and see what it does, right? So it's not a problem if you have like 1 or 2 outliers at the end. But if it looks like this, where you lose all the variability in the data, or a lot of variability. So for example, when it looks like this is bad. So when you have a small amount of intervals, and some intervals are very, very, very large, right? It could also be something like this, like we have a small one here and this. You also lose a lot of variability. You have so you have group 1, group 2, and this is group 3. You also will only have like 1, 2, and 3. Like if this is enough for you, if you want it that way, if you just want to see what these things can do, then it's okay. But generally, the less bins you have and the more there are in the bins, the higher the probability that you lose a lot of data. And it will look like this. So you take out all the variability of the income variable in this case, right? So everything that will help the model to predict, right? So what if, for example, people that earn less than 10,000, right? If they are interesting for your prediction, or people between 120,000, or if people that earn over 120 but less than 200,000, together with their bank statement or their age or their weight together, if this plays a role for your prediction, you will never know, because the only thing you know is 1. right? So you lose all this variability, all this information. So if it looks like this, you might want to consider if it's not on purpose. Like it could be that it is on purpose. Like even this could be on purpose, right? But then you would probably not use an automatic equal with binning, like with that formula, but you would set it yourself. Like you would say, okay, you would set the groups yourself. Like what you could also do, like you could manually do the bins. Like this is also something we could do, like as an option, like manual binning, right? This is also always an option where you really control the hyperparameter here, right? Where you really say, okay, I'm gonna do it like this. I'm gonna do like the first bin is like from 10,000 to 20,000 and so on. And then I will have an extra bin. Here then I will have a bin that says, okay, this is 200,000 to 1.8 million. And this is then the 1.8 to 2 million bin, right? So obviously this is not equal with now, right? So it's not fair, right? But you can do this as you can also do manual binning. Like you can always, but again, you have to know what you're doing, right? As I said, it's manual labor here. And equal height binning will get rid of this problem. Like you say, okay, equal height binning is changes it around. So now you have an equal height, and it will work until the last bin, obviously, because it doesn't always go equal. So you will just divide it up, right? So you just say, okay, we have equal number of bins, and so we're gonna put 4 in here, and then we're gonna close it up, and then we're gonna do the next bin. We put 4 in here, then the bin is closed. We make the next bin. So this is how the equal height binning is done, right? So you always have the same height. So you always know, okay, there are 4 in here, 4 in here, 4 in here, 2 in here. So in this case, you would say, okay, we're gonna have equal height. So we're gonna have the amount of people, right? So the amount of people will live, and then we would like put this up with the income, right? So this is the equal height binning example from that, by the way, so that you can like compare the two, right? And here the equal height binning example here depends, of course, on the number of people here, right? So if we have here like 20 people and this is like 1, then we would like easily do like 20. Then we can say, okay, how many bins do we want and so on, right? So let's say advantage of equal width binning, simple and easy to implement, produce a reasonable abstraction of data. Yeah, sometimes, right? Disadvantage, it's unsupervised, so we have no control over it. Where does n come from? And then sensitive to outliers. Obviously, you can see this is sensitive to outliers, right? So and we need to know like how many kind of data, how many data do we have, right? So do we take a sample and so on? So these are some things that we have to look at it. So if A and B are the lowest and highest value of the attribute, the width of intervals will be B minus A. So you have, for example, B, let's calculate it. This is A and B are the lowest and the highest value of the attribute. The width of all intervals will be, and N, of course, is the number of bins. So this is the number of bins, right? So the number of bins you have to set here. Like for example, I could divide this up as I want. Like because there is no limitation on the frequency. Like here there is a limitation of the frequency. So I start piling up 4. Then I'm going to create the next bin. I pile up 4. I'm going to do the next. I'm going to pile up 4. Right? So we can also use equal height binning. We now keep the frequency constant, change the intervals. But yeah, so the disadvantage here is like this is, of course, not very good for explorative reasons, like for interpretive reasons, right? But now at least the groups are fairly equal, right? So you can say the groups are fairly equal. So the amount of information lost is minimal, right? Because you have like all the groups are equal. So you will always get something like this rather than something like this, right? But as I said, if it's possible, you can also use a manual binning, but sometimes that's not feasible. Like, yeah, but if you say like, for example, I am interested in like some of the front groups, and then the rest can you can summarize it in a group like this. But usually, for example, when you write a paper on a master's thesis, you use this. It's hard to argue. The manual binning is hard to argue for, right? So you say, okay, here you have some sort of justice in each of them. However, the manual binning is just plain you, right? You say, okay, but you have to argue with what's your interest? Like, what's your prediction interest? What do you assume? And then we are back in statistics. Yeah. So sometimes this can be quite powerful. And now a way where this is definitely powerful. So as you saw, I did this with the X variables, right? With the features. But where it could have even more power and where it's done frequently is when I do this for my Y values, right? So I have a value of Y. And so what I can do is if I do it with the Y value, so if I have a numerical Y value and I use binning / discretization, so this is numerical, I'm going to transform this. I can transform this into an ordinal or nominal. Depends on how I see it, right? Usually it is ordinal, sorry. But I can define it in the software as a nominal if I'm not interested in the differences. And usually the methods that don't actually account for ordinal. So ordinal is kind of in a lost place in machine learning. I can tell you that. So nobody actually cares about ordinal data, right? It's more statistics thing. So, which is good for you because you don't have to think too much about it. But what I actually do is I have changed my problem now, my data science problem, from a regression problem to a classification problem. And this has huge repercussions. The battery of methods I now can use is changed. The methods of evaluation I now need to use, they are completely changed, right? So, and we will see this later on. So doing this with your target variable has high repercussions. And as I said also, sometimes, as it was said here, sometimes some methods require discrete values, and also, but the opposite, some methods cannot deal with them. Some methods cannot deal with them. And so either you have to turn them, so not really deal with ordinal values. So either you have to transform them into binary values, which you can easily do, which we will also learn, later. Like you can put every ordinal also in a binary variable. It's called dummy coding. If you haven't heard it, we will do it in a few minutes. So it could also be that some methods require discrete values, but also I have to say some methods cannot deal with this kind of ordinal discrete values. So they cannot deal with values that have 1, 2, 3, 4, 5, 6 and are not like an integer, where they are grouping variables, so where they are discrete variables. So there you have to be careful, because what it would mean if you just, so if you look at this variable, we have 1, 2, we have these numbers, 1, 2, 3, they are still numbers, right? So you have to tell the software that you're using. For example, Python, you have to declare the type of the variable. So for example, is it a grouping variable? It's called factors, I think, in data frames. It's a factor. Is it a factor? Or what kind is it? So factor is probably a multi-nominal variable. And sometimes they will say, I cannot deal with a factor that has more than 2 levels. So I have to change it to binary, right? So I have to transform this into binary. And the other thing you can do, you could just, I'm going to leave it at integer. But then they can interpret the differences. So they could actually interpret the difference between 1 and 6, right? And then if this is if this is not true, that 6 is really gets lower and stuff like this, then you are screwed, because you just assume that you can interpret the difference between 1 and 6, and that they are equally distant, so that the difference between 2 and 3 is the same as between 3 and 4, which we don't really know, right? So like we could assume if we use equal width binning, that's the beauty of it, because here it actually is. Because here all the bins are equal. We know this distance, so they are approximately equally distributed. Like this is the beauty of equal width binning, that you could actually would hurt less if you transform this, if you take it as a numerical variable into your Python code, because you can actually assume that the difference are fairly the same, right? At least from these values. Like, but you don't know if the groups are large. If the groups are large, like you don't know if it's 64 or if the group is, for example, 64 to 80. You don't know if it's 64 or 80, right? So you actually don't know. You would just say, okay, from the middle to this group to the middle of this group is equal, but you don't know which value of the group you got. So it could be this distance that is always the same, right? But it could also be the distance from 64 to 70, which is larger, but you don't know it, right? So you see problems over problems, and in practice, it's a little bit difficult to say. However, sometimes we do this specifically when we want to transform. So in practice, we would probably do this either when we want to look at the decision tree, right? Or we want to like transform our regression problem into a classification problem. Like this would be, to be honest, in practice, this would be the prime application of discretization, right? All right. So the next thing is not discretization, but it's called normalization, right? And as always, ask yourself, why do we need to do this? Why? Okay. So there are two reasons. The first reason I will explain with the thing that we're not going to learn, right? But wait, there is a question. Can I understand that when we use equal width binning, we should pick the expected number of bins based on the context business needs to experience? If the data looks off, we can just adjust the n to get better results. It's a little bit mixed. Okay, so listen. The n you choose, right? The n you choose. The problem is you won't solve this problem by choosing another n, right? Because you will like, even if you choose like 3 n's here, it will be a little bit difficult, right? So yes, you can choose n to adjust it, and it's the same as in a histogram. So I advise you to look at the histogram slide again to see how this will unfold. However, you have to imagine that equal width binning always defines this width. The width is always the same. So no matter how you choose n, the widths are always the same. You have more or less bins. So of course, compared to different widths, compared to different n's, the widths are not the same. But within one chosen n, the widths of each of these bins is always the same. So you don't necessarily circumvent that problem, right? But if you think like, if you have a hunch or an idea on reducing the data, you can either do manual binning, where you don't have to adhere to the same thing, or you can use equal width binning with an n that is suitable. But I think it's a disadvantage of an automatic method that you have to choose this n, right? Because then it's, in my opinion, it's not really far from manual binning. However, in manual binning, you have to define the bin width manually, right? Here you just have to define the number of bins manually. And whenever you have to choose something, unfortunately, unlike in a cooking recipe where it says you have to bake it for 1 hour at 200 degrees, we don't have this nice recipe here. So you are correct. And when you say we have to adjust it to the business case, and as I said, it's usually done with the target variable. And then it's easier for you to understand the business case. So do you want to classify? Where's your interest? Like, do you want to like divide the money up? Do you want to, for example, say, okay, if I have like transactions that are very where a lot of money is involved, I want to look at them. I want to classify these transactions. Basically, I don't care about the exact number of money. I just care about the classes, and then I want to see if they are there and that. So if you want to, for example, distribute material, for bank customers, right? So, or you want to address bank customers, you just want to know approximately in which kind of bin they are. Like it doesn't really matter if they earn like 10,500 per month, or if they like earn 15,000 maybe per month, or 15,201 per month, as long as they do not just earn like 1,050 per month. Like these, you would maybe not send for personal banking or something like this, or you wouldn't sell like you wouldn't sell them ETFs probably, right? But here you would say, hey, look at our cool ETFs, right? And it doesn't really matter, right? So this would be all one class. Like this would be rich or something, rich people, and this would be like poor people or something like this, or not poor people, but let's say normal people. They are not really poor, but normal and stuff like this. Like I think internally they call them that, but we could have nicer clusters like the smart sustainability person and the I don't know. They name the clusters pretty wild, but you can have like, and then you have like only these two classes, right? So from a context, then here you would basically define it manually, probably, right? So you would say, okay, this is what I want. I have an imagination about my business understanding. What kind of people do I want? So if I want to predict this, so this then you can use manual binning. Like you don't probably care about equal width or equal height binning. And sometimes you care about this. You will say, okay, I need this right now. I need an equal height or equal width binning, or I need it in this variable. I want it to be fair, so I don't run into this problem here, right? So I maybe use equal height binning. And yeah, so basically this is the answer. Like usually when in our usual cases here, I'm gonna be honest, you will do it manually probably, right? But then you have to justify it. But if you don't write a paper, like if you do it for your company and you have some domain knowledge, so usually this will be depending on domain knowledge, right? So this is like where domain knowledge plays a role, a large role, as you said already. Between drawing histogram and discretization data. Maybe I should watch the session. Yeah, it's basically the same. So the only thing is, so you have two steps, right? You have two steps here. The first step is here you create bins of equal width, right? It's basically the same. So in histogram, you also choose the n. In histogram, you also choose the n. So basically, histogram is equal width binning. A histogram is equal width binning, right? So histogram is equal width binning. If you want to draw a histogram, like it's equal width binning, where you decide on a number of bins, right? And then that's it, right? So if you look at the slide of the histogram, what we do is we only decide on a number of bins, right? And then we basically have equal width binning, because the histogram is like an automatic thing where it says, okay, we have two bins. So we saw like this, where we have a lot of data here and then some data here. So this is like n equals 2. And then we had this example where we had like, I think n was 5 or so. I'm not remembering exactly, but n was more like this, so 5 or 6 maybe. And then we had 3 in these, like we had 3 of each, and it looked like we had look something like this, and then we saw that this wasn't so bad actually, like as it was like here, I think. So it looks something like this. So we translated it somehow, right? And then it redistributed a little bit. But yeah, so this would be n equals 6, this would be n equals 2, and the width would be the same here always. I think it was like 20 years or something in the histogram, and here it was like 5 years or something. So yeah, so don't be confused. Histogram is equal with binning. Okay, so I hope this lifts your confusion. But yeah, you can revisit the slide any point. You will see that it's basically the same. Okay, now normalization. I want to do this, so we need to get moving a little bit. So I want to do normalization. So normalization, I will explain it. Actually, I explain it with a thing that we don't learn, which seems weird, but it's the best way to explain it. And then I can explain how it affects like prediction models and specifically machine learning, because it's a little bit harder. And I will need to revisit this when we talk about optimization, like in the next or probably the next lecture. So normalization, what it does is I want to give you an example why it's necessary. So let's say you want to look if two people are similar, right? So two people are similar. So you have a person one, person two. You have age and you have income. Very easy, like age and income. So this person is 24 and this person is 27. Okay. And this person has an income of 10,000 and this person has an income of 1,000. Okay, pretty easy. So it could be annual or monthly or whatever. It doesn't really matter. Let's just call it income. Okay. All right. So and now if I use a prediction model, right? If I use a prediction model, the prediction model will kind of try to make the factors in front of them, right? So if I use a linear model like this one, they will kind of make these factors scale with the magnitude of the values, inc, right? So but it's not like in an extreme way they will do this, right? They will do it to a certain degree because they want to generate this value. But it depends how good they fit. In an optimal case, you don't have to actually bother about this, okay? Specifically not in a regression. However, in other things like neural networks, a large difference in magnitude, and by magnitude, I just mean how long the number is basically, right? Magnitude, I get the following problem. So let's say I want to do not a supervised, but an unsupervised learning, right? And I want to cluster them, right? And now I calculate the difference between them, right? I calculate the difference between them. So I calculate the difference between 1 and 2. So when I usually calculate them, I'm gonna have like 2 minus 1. So I'm gonna have 27 minus 24, right? Plus what's it? 1,000. Just gonna make this minus 10,000, right? So, and this gives me 3 minus 9,000 if I'm correct, right? Because 1,000 minus, yeah. So, so this will be probably around minus 9,000, right? So the 3 we can like ignore. And this is, and what's the problem here? Like, what's the problem? This also can translate into the problem of a prediction model. What is the problem here? I basically said it through using this symbol. This symbol says it all. What's the problem? Like I calculated the difference between the two people. And what's the problem here? Analytical skill, guys. Analytical skill. Come on. What's the problem? Maybe it's better if I just try to get rid of this stupid thing here. What's the problem? Like I'm gonna make it easier. This is age and this is income. Right? So maybe this helps you out a little bit. Then look at this. This stands for 1,000, right? So 9,000. I can also write it out. It looks more. Maybe it looks cooler. Okay, different units. Yeah, there are different units. That is right. They are based on different units. Yeah, let's say we don't care about the units per se, right? So I actually subtract, you are right. So this is the core problem, but we won't get rid of the units. Like age will always be measured, could always be measured like in years, and income will always be measured in some kind of, like, we cannot get rid of this. Like we cannot say we transform income in years. Like it would be very weird. So, but I know what you mean. Like think more, think easier. Like Is it really the unit? So it's 3 years minus 9,000? But yeah, this is how it works, right? So this is how this is trust me, bro, right? So this is how differences are calculated. Like we can also have, it gets more complicated if these are from another scale. Like then we have, but even for that, there are solutions, right? Age and income is not linear related. Yeah, that actually doesn't matter. That actually doesn't matter, to be honest, right? Is negative amount allowed? Okay, yeah, sorry about that. Bop, 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 bop. Yeah, usually you square this. Just don't want to do the squared calculation. So usually you use like the Euclidean distance, right? And then it's like you use your Euclidean distance, and then these are squared. Okay. So this is squared. This is squared. So it's this squared, right? So I hope this helps. So it's yeah, we can get rid of this problem. Okay. I'm sorry. Yeah. Okay. Um. So basic, but however, so there are different ways. So you're not completely wrong. There are no negative numbers allowed. This is correct. But I could also use another distance. I could also use this one, right? Like this distance that just takes the non-negative. I mean, but yeah, you are correct. Distances need to be non-negative. This is correct. Yeah. I just was too lazy here. But yeah, technically you are correct. Age income are not linear related. The linear relation of them, what do you mean linearly related? I mean, the relation I don't care about here. Like, I don't have an interaction term here. I don't, I just, because this is, I compare them separately, right? I compare them separately. It's way easier. Different categories. Yeah, 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 kind of. Um, okay, easy for you. I'm going to give you another example. Right? I'm going to give you another example that should, I'm going to give you an example with person number three, right? Person number three is 72 years old and earns 2,000, right? So, and now I'm going to put up the distance between our beloved person number one and person number three, right? So, and this is again, this is now, you see, this is 72 minus 24. And then we have plus 2k minus, sorry, 10k, right? So, and this is like, this is all squared again, squared, squared. And this is approximately, again, minus 8, specifically now that it is squared, right? Specifically now that this is approximately minus 8k squared, right? So maybe that helps. One where is much higher influence than your, that's it, Jonathan, that's it. We got it. Maybe we should normalize the income by using 10 instead of 10,000. Perfect. Okay, size of scale is different. Income has much higher chance for outliers. The scale is different. It's good. Yeah. So the size of scales, this is exactly, it's just about the magnitude here, right? So income is much higher. Yeah, that also, I mean, it has chance. However, this is very important. Our solution will not jeopardize how the values are distributed. They will just crush the numbers. Like this is just a number crush. This is like when you, I don't know if you play like if you play games, it's like okay, like for example, I don't know if you know the game Diablo, right? So where you have like this little fighter guy or girl, and they have like a sword, and they start at level 1. Please don't judge me for my drawing. They start at level 1. And then you play like for yeah, with the newest patch, probably 10 hours, and you are level 100. You have nicer armor, and you have a large fire sword, right? Or some kind of flamethrower, whatever, right? And so here it deals like 25 damage. And here it deals like 1 billion whatever damage, right? Because they cannot scale their damage numbers. So, and The problem is now what they do is they do a stats called a stat squish. Like they squish it to try to make it more to reduce the magnitude, right? But they don't actually, what we don't reduce is like the relation between it. So an outlier will still be an outlier, like depending on how far it is away in terms of the whole variation. It's just that the variation in absolute values is very small, right? But it would still be an outlier, right? So you can think of this like if we have income here, right? We have if we look at income, and so basically I don't need this actually. This was stupid income. So this would be like we have all the values here, like this is exactly what you said. And here we have like an outlier, right? And here we have like 1,000. Here we have also 1,000. And here we have like this 1.8 million, for example, right? So this would be an outlier. So if after transformation, like after the whole transformation process, it would still look like that. However, the scale would be different. The values would be different. So it would be 0.15 maybe, 0.08, and here it would be like 0.89 or something, or 1.2. It depends on the method here. It depends on the method. But the relationship between these would still be the same, right? So it will preserve that relation. This is crucial, right? This is very crucial. Okay, and let's look at how we can actually do this. So there are a few methods. Where's my cursor? Sorry. So the min-max normalization. So somehow we need to have a look at like what is the range of the values. Obviously, we have to get some understanding of the scale here. And the first thing is min-max. So we take x as our original value. By the way, this table is beautiful for you. So you have an example here where this is x, this is the original value, right? This is the original value here. We have an example of h. So I really urge you after the lecture, which is over in 3 minutes, to study this example, right? And here you also have minimum, maximum, average, standard deviation, and you see the data after the transformations, right? So you can see here, this is min-max, like this is the original, this is orig, this is the original, this is min-max, this is min-max, this is z-score, this is z-score, and this is decimal scaling DAG, okay? So if you cannot read the small labels under them. All right, so let's go. Min-max is pretty easy. You take the original value, so the h here, right? So you take the h, and then you subtract the minimum, right? So that brings us basically, that brings your value basically, if it's somewhere here, you take it to the left side of the thing, and then max minus min. So, and then you scale it, and you can see here exactly what it is. What does that mean? Now I want you to, and this is like whatever we do, what are the two most extreme values of the min-max scaling? Like what and how you construct this, you take the extreme values of x. Now, if you have the minimum, right? So you can see here, the minimum is 28. The minimum age, this is 28. Like you can see it also here. Like this is the minimum age, this is the min, this is right here. The minimum age, and this is the maximum age. Max, you can also see it here, right? Maximum, minimum. Now, if we have the minimum, then what is this? Then this becomes 0, right? Because min minus min is 0, so we don't care about this unless it's, right? So this becomes 0. And we can see it here. This is 0. So the minimum value of the scale is 0. So this is the minimum value. And the maximum value, so we have max minus min divided by what? Max minus min. And the same divided by the same is 1. Exactly. So the maximum value is 1 given at the max value. So this means that min-max normalization always scales the values between 0 and 1. This is very important. Not every scaling does that. I cannot stress this enough. It's not like every normalization puts them between 0 and 1. This is absolutely false. Min-max does, the others, they do not, right? So, or at least z-score does not, right? You can see here. Okay. Z-score, the motivation for Z-score comes from the standard normal distribution. So this is not by min-max scaling, but it's rather by standard deviation. So it looks like how the data deviates. And based on how the data deviates, so if it's really small, then it doesn't squish too hard. It's a deviation. So we take the value and we subtract the mean. So again, first we position it, like here, we position it, we subtract the mean, so we know if it's right or left from the mean. So this is important. And then we're gonna divide it by the standard deviation, right? So basically what we do is we get a more, like we try to get a more symmetric thing, Z-score. And this also happens to be that we can get negative values, right? Because to the left and to the right of the mean. So we position them and want to know whether they are to the left and the right of the mean, and we squish them by dividing through the standard deviation, right? So this is the idea. So we get the difference between the mean. So if the mean is rather large, we just get the differences. So instead of like having the whole 10,000 thing, if 8,000 is the mean, so the value gets smaller, then we scale by standard deviation. Now, and the last but not least is decimal scaling. So I think someone actually suggested that. Yeah, I think Jonathan, you suggested it. So congratulations, Jonathan. You basically invented decimal scaling. So what you said is basically decimal scaling. Maybe you should normalize the income using 10 instead of 10,000. Yeah. And so this is basically, you have like the small, J is the smallest integer. So max X is smaller than 1. So basically you have a range from minus 986 to 970. So integer, we have three integers, 1, 2, 3, right? So how many integers make up the number? And then we squish it by that. So we squish it exactly by that. And yeah, that's it. So we just divide them by 100 here. Yeah, so 1,000, sorry. Just divide them by that number, right? So you can say 10 to the power of j. So j is the number of integers. So x, 10, we have 3. So it's 10 times 10 is 100 times 10 is 1,000. We squish it, and then we do exactly what Jonathan basically said in the chat, right? That's it. Okay. So that's the easiest one. And you can see here, you can have a look at this. And yeah, you can also see here that this just scales by dividing it. So there is no real min and max. So there is no real 0 and 1. This is very important. So this is the only thing where we can basically say this, the min and max of the new scale. Like here, we don't basically know. Like we know the min and the max is still the min and the max. And here, the min and the max is also still the min and the max. So we can see it right here. So the max value is still the max value. As I said, we will preserve this, right? As you can see, the max is always the max and the min is always the min. It's just a stat squish. Now, instead of 10,000, we have 0.44. Okay. And yeah, next time we will work on this. So I will give you another explanation why this is needed, a short explanation, because we will revisit this in learning. But what I can tell you is with large values, the whole optimization process of finding these parameters here, like we need to, our goal in machine learning is to find these parameters. These are, by the way, called parameters, not hyperparameters, because the computer does it for us. More on that later. However, we need to find these parameters. And it turns out with having like large magnitude values, the computer has trouble doing that, right? That's basically it. All right, perfect. Okay, see you next week. Enjoy and enjoy the rest of the week. And as always, if you have questions, please ask ahead. Thank you so much.